This is my Lab 5 physics report. The purpose of this lab is to compare the magnetic braking effect in an experiment with a computational model. I used 4 principles in this lab, including Faraday's law, magnetic flux, magnetic dipole field off axis, and magnetic force. I found a 1.2% difference in timings between the experimental and computational models. The first principle I used is Faraday's law, which shows a relation between induced non-coulombic electromotive force and a time-varying magnetic flux. The derivative of the magnetic flux in a conducting loop is equal to the induced voltage in itself. The second principle I used was magnetic flux, which is the B field over an area. The third principle I used was magnetic dipole field off axis, which is an equation that gives the strength of a magnetic field in teslas anywhere relative to the magnetic dipole when the distance from the dipole to the observation location is much greater than the distance between the dipole ends themselves. The fourth principle I used is magnetic force, which gives the resultant force when you cross a moving charge or current with a magnetic field. For the experiment, the system was the magnet, and the surroundings were the aluminum foil tube and Earth's gravitational pull. The initial conditions were an initial velocity of 0 for the magnet, a magnetic dipole moment of 1.53 joules per Tesla, tube length of 30 centimeters, foil thickness of 2 centimeters, an inner radius of 1.5 centimeters, and a mass of 23 grams for the magnet. I held the magnet over the tube of aluminum foil, which I held in my hand, and it had a known thickness and height. I dropped the magnet then into the tube, and I measured the time it took for the magnet to exit the bottom of the tube after I dropped it. I repeated this 5 times to get 5 different timings and averaged them to get an overall time. I assumed that the bar magnet acted as a magnetic dipole, which was measured with the formula that I used on the previous slides, and the air resistance had negligible effect on the net force experienced by the magnet. I found an average time of 3.124 seconds for the magnet to drop through the aluminum foil. These were the observations that I had, each drop and then the average. For the coding, I used a modified Python code for the model, and I had the same initial conditions as the experiment. The code visualized the magnet dropping down the tube and displayed its velocity from the moment it dropped until it exited the tube. It calculated the time it took to drop through the tube, and it made the assumptions that only gravitational magnetic forces acted on the magnet, and that the foil tube could be modeled as a series of stacked rings with known dimensions and resistances. It used the formula for magnetic field strength off axis to calculate the magnetic field strength at the opening of each ring, and then it calculated the change in magnetic flux at each ring to find the induced voltage. The current in each ring was then calculated from the previously found induced voltage, which allowed the magnetic force experienced by each ring to be calculated. The sum of magnetic forces in all rings was used as magnetic force experienced by the magnet when falling down the tube, which is then added to the gravitational force that the magnet experienced to get the net force. This is the coding that I used. On the left side, you can see the initial conditions and functions that I used to calculate the induced voltage at each ring. The first one is finding the B field at any given observation location from the magnet, and the second function calculates the change in magnetic flux over time using the B field and the known values of the rings. On the right side, there's a looping function that calculates the net force experienced by the magnet and updates its position and velocity. At the top, you can see that the force of gravity is calculated, and then after that, each ring is iterated through, and the magnetic force that each one experiences is summed to get a total force that acts on all of the tube, which is the same as the force that acts on the magnet, which is then added to the gravitational force to get the net force. Here's the coding output. On the left, you can see a snapshot of the magnet falling down the tube, and on the right, you can see a graph of the velocity versus time for the magnet. Comparing between the experiment and the model, the experiment took 3.124 seconds at an average from 5 trial runs, and the simulated time took only 3.086 seconds. The experimental time took 1.2% longer than the simulated time, which is remarkably close for such an experiment. On the simulated velocity versus time graph, you can see that there was an initial spike in speed that was quickly decreased, and it plateaued until the magnet exited the tube, at which point it sped up. The net force was therefore 0 between 0.3 and 2.8 seconds, and the spike was likely the braking effect of the magnet. Possible sources of error include air resistance that could have increased the time in the experiment compared to the simulation, since it would act against the magnet's speed, and that's a systemic error, and inaccurate measurements from human timing using visual observations and a stopwatch, which would be random error. If the resistivity of the conductor were reduced to as close as possible to 0, then the braking effect would be a lot stronger compared to larger resistivity, because the lowered resistivity would result in a stronger current, which means that the force experienced on the current would be greater because of the equation that I previously showed. If holes or slots were cut into the tube, then this would decrease the ring currents in the model because the total change in magnetic flux experienced by the tube would be a lower absolute value as the ring area that the magnetic field is and made fewer rings possible. Thank you.